And next we have Sabiq Islam, who will be presenting. Hi Sabiq, can you share your screen?
Yeah.
Okay. Cool. I'll set the timer and it's all yours.
Okay, cool. Hi guys, my name is Sabiq Islam and I'm a fourth year undergraduate at UT Austin under Dr. Jean Ann Corvia. And I'm happy to present our work with TSMC on predicting novel tunnel barrier materials for magnetic tunnel junctions using language models and first principle screening. So to preface our study, I want to talk about the MTJ for those who might not be familiar with it. So the MTJ, or magnetic tunnel junction, is primarily comprised of two ferromagnetic electrodes separated by thin insulating tunnel barrier. So when the magnetization of these two electrodes are parallel, an electron can tunnel through easily, whereas when they're anti-parallel, that tunneling is suppressed. The difference between this parallel and anti-parallel magnetization is what gives rise to what is known as the tunnel magnetoresistance. And during the low resistance state, how easily a spin-induced electron can tunnel through the barrier is known as the resistance area. And these are two of the key metrics for defining performant MTJs. So as outlined by Western Digital and Seagate, for hard disk drives achieving 4 terabits per square inch, the storage density needs to have a RA beneath 0.1 ohms micron meter squared and magnetic resistance above 100%. So the canonical tunnel barrier for magnetic tunnel junctions is magnesium oxide, and this is because it provides this delta 1 symmetry filtering, which enables high transmission. However, a really big bottleneck with MgO is its high band gap of about 7.8 electron volts, and this causes it to have a very high resistance area product. So when we try to scale down MTJs, it becomes hard to maintain a low RA, and it also creates wafer variability and creates pinholes, which leads to a poor MR. So many studies have been done to find suitable alternatives for MgO. Most notably, one of them is scandium nitride, due to its ability to achieve a lower RA. However, the issue persists of balancing a high TMR with low RA. So to overcome this materials bottleneck, we propose a novel framework that couples both NLP models and density functional theory to accelerate materials discovery. Our pipeline first starts with extracting data of materials science abstracts from multiple reputable journals and then pre-processing them so they're suitable for the machine learning models. Next, we use several models to train on the data and then prompt it to get a down-selected list of materials to be further evaluated. This list of materials is then evaluated using density functional theory, where the TMR and RA are benchmarked against that of MgO to see if we can achieve a higher TMR and a lower RA. So to start on the ML side, we adopted an approach similar to that of Dr. Sharon Sayed's for identifying high spin orbit torque materials. So this uses a model called word2vec, which is a shallow neural network that creates word embeddings from the text and compares their distance and latent space using cosine distances. So words that have a high cosine distance with our sort of anchor terms, spin-dependent tunneling, tunnel magnetoresistance, and spin filtering, are known as materials that could be good tunnel barrier candidates. So from here, we can see that materials with a high correlation score are correctly predicted as tunnel barrier materials. Seeing as though MgO is predicted as the best, it shows that our model correctly trained on the data. But interestingly, we also get some other candidates, such as dysprosium nitride, and this one here, niobium nitride, magnesium oxide, and niobium nitride. And this one stands out because this is actually the sort of configuration you'd see in a Josephson junction. So this underlines how our lead pipeline is able to extract from adjacent fields and apply them to magnetic tunnel junction tunnel barriers. So after exhausting this model, we turn to Google's other model, BERT. So the way BERT works is that it will use the BERT mask language model. And the way it works is that it masks out a word and then it looks at both directions and tries to predict the word based on that. So we trained our model on that in order to capture deeper contextual relationships within the text. And then with that, we created mass sentences to prompt the word and get candidate barrier materials. However, an issue or a shortcoming with this is that some of the material predictions were non-candidate names. So to limit that, we used Llama 3, the generative model, and prompted it to give us a list of feasible tunnel barrier candidates, and then use that list as a way for BERT to select from and predict masks from. So after curating a list from both of our approaches of just Word2Vec and Materials BERT coupled with Llama 3, we then used human in the loop down selection to further reduce our list based on features such as having a band gap above 0.3 EV or whether it's cubic. And then we got our list ready for DFT evaluation. So our main candidates are such. We have magnesium oxide and scandium nitride as our two main benchmarks. We have the Josephson junction niobium nitride configuration, DYN, and then from Llama 3 materials BERT, we have titanium nitride, tantalum nitride, vanadium nitride, barium oxide, and zinc oxide. So the first thing we did was examine the electronic structure. From our benchmark MGO here, we can see that from gamma to X, the delta 1 symmetry path is present. And when we look at scandium nitride from gamma to X, we see that the delta 1 symmetry path is down here, but we also see that it introduces this delta 2 prime symmetry path. And what's interesting about this is that it enables even more spin polarized tunneling to the d orbitals, which means higher transmission. So notably, when we look at two of our candidates, niobium nitride and titanium nitride, we see that they share a very similar electronic structure to that of scandium nitride, but with this Fermi level pinned within the conduction band. So this suggests that these two materials, along with the other nitrides, can also support both the delta 1 and delta 2 prime symmetry filtering. So with this in mind, we went ahead and calculated the TMR of our main candidates. So from the pristine barriers, or pure material tunnel barriers, we see that magnesium oxide persists as the best, with zinc oxide coming in at a close second. However, when we tried our Josephson junction configuration, we see that for niobium nitride, it is a sizable TMR, but when we replaced it with scandium nitride and titanium nitride in the same configuration, due to the similarities in the electronic structure, we see that the TMR actually exceeds that of all the materials in this list here, with scandium nitride even being more than double what magnesium oxide was. So to further evaluate these, we varied the configuration of the oxide and the nitride within the tunnel junction. So we see here that when we only have a monolayer or a single layer of the nitride between the Fe and the MgO, the TMR is the highest. But when we thicken this, it decreases. And then when we keep the interfacial layers thick but increase the oxide, there is somewhat of an increase. But when we try half-half designs or other configurations, the monolayer still persists as our highest TMR configuration. So to further evaluate this monolayer configuration, we try to look at this pattern we saw here with thickening the oxide. So that's exactly what we did here. So from here, I'm benchmarking MgO, which is in green here, which is just pure MgO, against monolayers of titanium nitride and scandium nitride, where I'm keeping one layer at each of the interfaces while thickening the oxide in the middle. So what you can see here is that across all the thicknesses I tried, titanium nitride and scandium nitride consistently outperform MgO. But what's interesting is that for more thin layers, scandium nitride is the most performant. But as we go higher, titanium nitride dominates at larger thicknesses. This suggests that scandium nitride would be optimal for thinner barriers, whereas oppositely, titanium nitride dominates at thicker ones. So looking at our performance frontier of our simulated MTJs, we of course benchmark our two main metrics, the TMR and RA, against our benchmark MGO here, which is outlined by this black dotted line. So materials in the red region indicate those of poor performance of a high RA and a low TMR, whereas those in the green are a high TMR with a low RA. And we can see here that the titanium nitride and scandium nitride hybrid structures consistently outperform our MgO benchmark here across all thicknesses. And more noticeably, we also saw that having the double titanium nitride at the interface also performed quite well. And like we saw before, zinc oxide performed well. But our other configurations and our other predictions made by our models like tin aluminum nitride and vanadium nitride, DYN, they did not perform as well. So in conclusion, we were able to see that our lead pipeline could successfully enable a high throughput method of materials discovery beyond the traditional intuitive sense. And then with how it was able to extract from adjacent fields and using efficient computational resources. From our results, we saw that the hybrid scandium nitride and hybrid titanium nitride are able to outperform the canonical tunnel barrier MgO. And this shows that we have a viable and more scalable path toward achieving high performance MTJ devices suitable for magnetic sensors and hard disk drives. Our future work would be experimentally evaluating these hybrid structures. And this work is currently under review. So I would like to thank my PI, Dr. Incorvia, as well as TSMC for their funding and support, and also the Texas Advanced Computing Center for their compute resources. Thank you.
Thank you, Sabiq. Very interesting talk. Great use of I guess. So do you have any questions from the chat or someone want to raise their hand? No? Okay, I think it's a very cool project. This is my first time seeing like something done by this. So just to make sure I understand it, like for the language model part, that's where you feed in a lot of literature, and then you try to like predict what would be the material to test. Is that correct? And
Yes, exactly.
and then based on the prediction, then you try to apologize for the very, very funny timer. So then after the prediction, then you do DFT calculation or simulations to actually see what the TMR should be. That's the pipeline. Is that?
Yeah, we use DFT to evaluate it and compare it against MgO. Correct.
I see that you benchmark to MGO, but I'm curious, do you have a benchmark of your large language model? Because I would have think like, yeah, of course, MGO is like the benchmark word commonly used, but for your for your large language model, how does the result that is spit out, how does it compare to maybe like ChatGPT searching the web, spitting it out, or is there like a benchmark that you could do something like this?
Yeah, with regards to comparing to other ML models, it's a bit of a tricky situation just because this approach is so unique. But something we did do to verify that our models are actually training on the data properly was that we set up very simple prompts, very obvious ones to see if you could correctly identify more obvious materials. So like we saw before with Word2Vec, obviously MgO came up first, but also for Llama 3 and for materials BERT, we gave it very simple prompts to see if it could correctly identify MgO just based on the data it was trained on, and it could do that, yeah.
Cool. And also one thing that I was thinking while like looking through this pipeline is that you can only like maybe it can only spit out result that people have mentioned before in the literature. So there seems to be like a limitation on the kind of materials that you're able to get out from this process of doing maybe like a smart way of doing literature review. Um, does it give you like any additional like maybe like a smarter way of suggesting some new materials that's not covered in the literature review, things like that?
Yeah, I think the biggest idea of this pipeline is being able to identify like hidden patterns in the text, like I was saying. So our text spanned from the 1960s through the 2020s. And obviously for a regular human being, be able to span all that text, read it, and extract patterns between the different papers would be very hard. But our model was able to do that with how it was able to identify that Josephson junction as our most performant candidate. So the whole idea is about, yeah, just finding hidden patterns across these decades of text. And it really offers a scalable path as you could feed in more data or even apply it to other fields aside from magnetics. If you prompt it differently, it give it a different variety of papers and journals.
Okay, cool. Thank you. Let's thank Sabiq one more time.